Designing a direct-to-device network is only the beginning. Once the satellites are up and connected to the ground, the thing has to run continuously for millions of users, while every base station in the system is moving. Building one is an engineering challenge. Operating one is a continuous optimization problem. Start with mobility, which is the hardest operational problem here. In a terrestrial network, the user moves and the tower stays put. In D2D, both can be moving at once, and the satellite is doing 7.5 kilometers per second. So every user gets handed to another satellite eventually, even standing perfectly still. Handovers stop being exceptional events and become normal operation. The network predicts trajectories, estimates beam availability, and prepares the next satellite before the current link expires. Then there is beam scheduling. A satellite generates many independent spot beams, and those beams are a scarce resource shared among thousands of simultaneous users. The scheduler continuously decides which beam serves each user, how much bandwidth each one gets, which modulation and coding scheme to apply, and how to distribute transmit power. And because digital beamforming can move the beams themselves, scheduling includes beam geometry, not just radio resources. Capacity is where those decisions bite. Every beam has finite bandwidth. Every satellite has finite power. Every feeder link has finite throughput. So operation becomes an optimization, balancing user demand against available spectrum, satellite power, feeder link capacity, and quality of service commitments. During congestion, priority traffic, emergency communications, above all, may receive preferential access. Dynamic allocation is what lets a constellation maximize overall service quality despite hard limits. Running hundreds or thousands of spacecraft demands continuous monitoring. Operators supervise satellite health, antenna performance, RF power, gateway status, feeder link quality, traffic loading, software status, and orbital position. A modern operations center is a strange hybrid: conventional telecommunications monitoring and spacecraft operations at the same time. Instead of watching routers and base stations, you are watching vehicles that circle the Earth every 90 minutes. Failures are inevitable. A gateway loses connectivity. A feeder link is interrupted. A satellite becomes temporarily unavailable. Interference degrades a beam, so the network has to detect these automatically and redistribute users toward alternative satellites or gateways. This is where constellation redundancy earns its cost. Because several satellites are usually visible at once, traffic can often be rerouted with no user intervention at all. Increasingly, all of this runs on software-defined networking and network function virtualization. Functions that once lived in dedicated hardware now execute as virtualized functions on cloud infrastructure. That lets operators deploy new services quickly, optimize traffic dynamically, update functionality remotely, and scale with demand. The satellite network becomes one part of a much larger software-defined platform. Put it together, and here is what happens every second. The network predicts satellite motion, schedules thousands of beams, allocates radio resources, coordinates gateways, balances traffic, monitors spacecraft, executes handovers, maintains synchronization, and routes data into terrestrial core networks, all of it automatic. And the user simply sees a familiar cellular connection with a couple of bars of signal. To close, building a D2D network is an engineering challenge. Operating one is a continuous optimization problem. Every second, the system coordinates moving satellites, gateways, radio resources, and terrestrial infrastructure so that millions of users experience what appears to be one single, seamless cellular network